a brief overview of sustainable operations by Bill Weihl, our green energy czar, and then followed by a discussion of water usage in data centers and another very cool video of an actual Google data center internals. So Bill, please take it away.
Thanks, Urs. Okay. So this actually seems particularly appropriate given the discussion at the very end of the last panel and some of the comments that Ken was making. One of the questions would be, what is sustainability, and does it really matter? Should we be thinking about it? And I think today is about energy efficient data centers, so the focus has really been on energy. We've certainly heard about water and some other issues. Hiding behind energy, implicit in that is the climate impact of producing all that energy. I believe, and I think Google believes, that most people at Google believe that we have a responsibility to worry about sustainability, to worry about the climate. And that I think Olivier was absolutely right, that if you think about this, you might initially think, well, it's going to cost too much, so I can't do that. But if you think about it, you can sometimes come up with creative ideas that turn out not to cost too much. Or the things that help you with sustainability turn out actually to save you money, in which case they would have been a good thing anyway. So I think it's important to focus on this issue, maybe not to have everybody in your organization focus on it, but you should be thinking about it. So what is sustainability, though? So I did a quick Google search. I don't think I'm allowed to say I Googled it, but the lawyers will tackle me or something to say, what does sustainability mean? And I'm not going to read these, but I think there are a couple of points to take from these. One is it's about not depleting resources. So preserving the planet's ability to support us and our civilization and ecosystems into the future. And then the other, which really relates to business, is that sustainable businesses are about what people have called the triple bottom line, which is a phrase that, to be honest, I kind of hate. But it's about the point that if you want to have a sustainable business, well, you've got to worry about economic sustainability and growth and prosperity for the business. You've got to worry about social aspects for the community that you're in, and you've got to worry about the environment. All those are important. You forget any one of those, and in the end, it's probably not actually all that sustainable for the long term. Okay. So I want to talk just briefly about best practices, then I'm going to touch on a couple of issues, and then Joe is going to dive deep, into the deep ocean, more or less, on the water side. So we've heard a lot of this today already, so I'm not going to dwell on it too much. Clearly, measuring is important. If you want to be more sustainable, you got to figure out what to measure, and you got to measure it. If you don't measure it, you can't manage it. Given measurements, you can prioritize. And in fact, to decide what to measure, you need to do a first level prioritization, because some things are not significant enough to be worth the time to measure or to measure very accurately. So there's prioritization that's going to go on all along the way. And we've been doing this. I've been at Google now for 3 years. We've been gradually focusing on more and more aspects of our operations and how to make them more sustainable. You really need to think about all the resources. So we talked a lot today about energy, and we talked about water. But you got to worry about wood and metals and any other materials that are used to build or produce your products and services. And you've got to look at the entire supply chain, upstream, your suppliers, also downstream, your users, the full life cycle, to understand what are the environmental impacts, what are the social and economic impacts, et cetera, et cetera. Okay. Embodied energy is a phrase that people use a lot, but the energy basically used to make something. So you buy a laptop, the embodied energy in a laptop is more than the energy that will be used during its operational use phase in its lifetime, okay, which is kind of striking. That's because it's a very energy efficient device. It's probably true for a cell phone even more so, right? But it takes a lot of energy to make the stuff that goes in it. So that's something, once you've made the thing itself energy efficient, you better start thinking about, well, what about all the energy that went into producing it? You need to aim for continuous improvement. I think it was Olivier who said this just a minute ago. It's not about the destination. Perfection is not the goal. Improvement is the goal. Getting to a lot better than where we are today is the goal. And then one of the things, and this gets to sort of the social aspect of the triple bottom line, one of the things we focus on a lot here is keeping our employees healthy and happy. We try to build workplaces that have good indoor air quality, good lighting. In other ways are places that are comfortable and healthy places to work, and that are fun places so people are happy. That helps them be healthier, et cetera, et cetera. And that's an important thing. I'm not going to focus on that, though. If you saw the cafes, you may have seen, I don't know, do we have any of the big bouncy balls in here? Massages, et cetera. All that stuff is good for making sure that we stay both healthy and happy working here. So I want to touch on two issues. The first one is e-waste. It's a growing problem. I don't need to go into why it's a problem. We produce a lot of stuff as an industry, and historically over the last decade or two, a lot of it's gone into landfills. A lot of it has gone into landfills in developing countries. This is a disaster. What are the solutions to the problem? Well, it's what I would call the 4 R's. Reduce, so don't just buy new stuff because it's new and you can. Buy it because you need it. Reuse what you've got, and either yourself or get others to reuse it. Repair it if it's broken and then reuse it. And then recycle whatever's left. Don't just landfill it. And whatever, sometimes there's going to be some amount of stuff that you can't do any of that with. Well, then you got to find some responsible way to dispose of it. So what are we doing here at Google? When our servers reach the end of their useful life, for us, well, first of all, we reuse 68% of the material in retired servers. Memory chips, CPUs, disks, other stuff gets reused either by us or by others. The remainder is recycled into raw materials essentially by smelting it to extract all of the useful materials, the precious metals, et cetera, and to get rid of the rest in a form that can be safely and responsibly disposed of. We don't throw stuff in open landfills. We don't just incinerate it and have toxics go up into the atmosphere. We don't export it to developing countries. And this is true. So if you look at what's reused or recycled, it's basically 100% of what we get rid of. And we don't just store stuff in a warehouse waiting for some future solution. If you look at what's happening in the US, the EPA estimated that in 2006, only 18% was reused or recycled. The rest was landfilled, incinerated, or stored, waiting for some future solution. So solutions are here today for this problem. Lots of other companies actually in the industry, I think, have made huge strides in the last 2, 3, 4 years on actually getting more toward this point. But there's still an awful lot of people who aren't taking advantage of those. Companies that buy equipment or individual consumers, they don't have good ways to dispose of stuff responsibly. So I think that's an issue that's been, I think, a growing problem, but one where maybe we've crested the hump and are coming back down the other side, where as an industry, things are definitely improving a lot. The other thing I want to touch on, and this is going to be really quick because you've heard about it from James and a bunch of other people, is water. This actually is something that is a big issue in the western U.S. There's a huge drought coming, and I just put this headline up here because it sort of struck me that ESPN had an article recently about the coming U.S. crisis in water policy. It never occurred to me ESPN would actually be talking about that, but I guess if you're a sport fisherman, you'd understand that. But the western U.S., there's a disaster coming, and we're entering what may actually be a historically really bad drought. And the water allocations from the Colorado River and other watersheds were based on a time of exceptionally high historical water levels. So the supply and demand don't match. And this is a problem for anybody who uses water. Google, anybody else who uses water for any operations, much less individuals. In fact, Lake Mead, there's a prediction came out of Scripps about a year ago that the water in Lake Mead could effectively dry up in terms of what it's used for, power generation, irrigation, et cetera, by 2021. 50% chance of that happening. That's a disaster. So water is clearly something we got to worry about. Climate change may make this a lot worse. And I think James is absolutely right. If you can avoid using water completely, that is by far the best solution. Or if you can't, then minimize the amount. And Joe's going to now talk about what we're doing on the waterfront. So, Joe.
Thank you. So good afternoon, everyone. My name is Joe Kava. I'm the Director of Operations in our data center group here in Google. And I want to thank Bill for introducing the sustainability topics to us. And I also want to thank James and Olivier and Dean and Andrew this morning, who made some of my points that I'm going to be making in this presentation. So I'm glad to see that the donation envelopes that I gave to you guys this morning actually made it into your pockets. But I am a sport fisherman, and I do read ESPN, and I watch ESPN, and it is important to me. And I do want to spend a few minutes delving into sustainable water management with respect to data center operations. Dean, I'm going to argue with you a little bit. I think the big elephant in the room is water, and maybe not only application utilization. I think that, in fact, this is the next big issue that all of us are going to have to address. I think as a whole, our industry has done a very good job over the last couple of years, specifically with leadership from the Green Grid and the Uptime Institute and all of you in this room, that we've been focusing on power and power consumption and energy efficiency, and that's excellent. I think the next thing we need to turn our attention to is what do we do about the looming water crisis, and how are we going to address that with respect to sustainability for our data center operations. So a few key overview messages. I really like the way that Olivier was discussing that it's not simply just about ROI, but it's about doing the right thing environmentally. And I take it a step further. I think it goes into the TCO model in that, what about business continuity? And that is a very, very big driving force in your TCO model. So I think that business continuity factors are really driving some of our considerations for water resource management. I don't think that any of us would argue that water resources are becoming more scarce. And as such, I think the link between data centers and water resources is going to be more plainly evident to a wider audience, just as the link between power consumption and data centers has become more widely obvious to a broader audience. And with that will come public scrutiny and perhaps political intervention. Andrew alluded to it this morning. Water consumption in data centers might be regulated. I want to talk and maybe present a little bit of a different viewpoint here, in that reducing water consumption in data centers is a great objective that we should all be looking for. But I think there's another opportunity, and at the right size and scale, I think that reuse water and reclaim water use in the data center is an opportunity, and I'm going to get into a little bit more details about that, about what we've been doing in that regard. I think that all of us agree that we're probably in this room because we care about the environment and we care about the impact and the climate change, and water use and water consumption has a big impact on that. So I don't think there's really any argument about the impact of depleted water resources and the effect of our environment. There are some other risks that I think that I propose we need to take into consideration when we're talking about sustainable water resource management. Those risks are availability due to drought or due to regulatory action. Urgent access. It could very well be that your data center expansion, the gating item for that expansion is the schedule of your local water authority for upgrading their capacity in their lines. And also competition from neighboring developments, right? So if there's another big company or another big industry coming into the neighborhood and they're going to be competing for the same water resources, you may actually wind up having to reserve and pay reservation fees for access to that water for your data center expansion that you've planned. And future costs. Really, these capacity upgrades, especially as water resources become more scarce and more difficult to extract, the upgrades that the utilities are going to have to do to get at those water resources are going to be very expensive, very costly, and we all know that those costs will be burdened by the consumers. But is the situation worsening, or is it just status quo? So this was taken from the Sandia Labs report to Congress, and it's a reprint of a table that shows water resources at various different regions across the United States. And in each of these cases, the groundwater and the surface water declines are really just staggering. But at the same time, the USGS is reporting that the total water consumption in the US in 2000 was approximately the same as it was in 1990, even though the US population had grown almost 13% during that same period of time. And they're attributing that mostly to better technology, advancements in technology, and conservationism. So if the total consumption in the US is staying the same, is the problem really getting any worse? Well, maybe. So these are two side-by-side shots of Lake Lanier in Georgia, taken from March of 2007 on the left to February 2008 on the right. And you'll see how much the water level has receded in just that 11-month period. (2007) may have been a particularly dry year, though, so maybe it was just a temporal effect. Maybe not. This is another lake in Georgia also in 2008, just this last November. And what you're seeing here are boat docks. Unfortunately, these were not intended to be dry docks. These were actually at water level just the past couple of years previous. So the situation may in fact be getting worse. Just last week, the Wall Street Journal published a very timely article in which they claim that the total water withdrawals in the United States, of the total withdrawals, nearly 50% of that is used in the electric power generation industry. Now, most of those water withdrawals used for electric power generation are returned to the waterways at some point, but still 2 to 3% are lost through evaporation. That's about 1.6 trillion gallons of water a year lost to evaporation, or roughly the equivalent of about 17.5 million US households worth of water use annually. So why do we care? And how do data centers fit into this? I'm going to argue a little bit with James on this one. You used a 15 megawatt example and what the power or the water consumption was for cooling tower evaporation and blowdown. I'm going to claim that your numbers are wrong. The reason I'm going to claim that is because if you look at the embedded supply chain and how much water was consumed in generating that 15 megawatts of power, that the numbers are far more significant. I normalized it to a 10 megawatt IT load or a 10 megawatt cooling tower load. The average data center would use about 150,000 gallons of water a day to cool that load in evaporation and blowdown. Upstream of that data center, the same 10 megawatts consumes about another 480,000 gallons of water. So the total embedded supply chain is over 600,000 gallons of water per day for that 10 megawatt cooling tower load. An interesting fact that as we were going through this analysis kind of struck us is that because of the overwhelming influence of the power generation factor in that consumption, that the average waterless data center would actually consume about a third more water than the Google evaporative cooled data center with, all things being equal, same 10 megawatt normalized load and all that. And of course, PUE is a driving factor in there, but it really is because of the power consumption ratio. So in fact, what we've been doing, reducing our PUE, is one of the most significant terms you can use to drive down your overall water consumption as well. Maybe not something that is intuitively obvious, but all the work that we've been doing on getting more efficient with power consumption is helping with respect to water consumption as well. So what's the cost of all this water? I'm going to argue that it's meaningless. It's trivial. That right now water is cheap. And the regional prices range anywhere from less than $1 per 1,000 gallons to more than $5 per 1,000 gallons. It just doesn't matter. It is cheap. It doesn't show up on the top 10 things on your expenses. I think that, James, when you talked about the OPEX breakdown of a typical data center, water doesn't show up on there. So your CFO might not be targeting what are you doing about water reduction because it's costing me a fortune. So I argue that the cost of water is trivial from a simple OPEX standpoint. The cost of water from a business continuity standpoint and the access to that water, I argue, is extremely, extremely expensive. So what is Google doing about this? Since our data centers program, our internal data centers program began in 2005, we've constructed 2 sites that are 100% self-sufficient for water cooling process load. One facility uses a side stream plant to treat the effluent from the public utility and use that in our cooling towers. Then we retreat the water and release it back into the public utility. A second site in Belgium, and I'm going to give us a video tour of this in just a moment here, uses water from a public industrial canal. We treat the water in an on-site treatment plant, and we use that for our cooling tower and our process load. We are also currently constructing additional sites with water retention ponds so that we can reuse stormwater, recapture and reuse that stormwater. And we've been really, really focused on lowering our PUE, lowering our total energy consumption as a driving component in lowering our impact on water use. So our goal, our company goal, is that we want to achieve 80% self-sufficiency for data center water use by the end of 2010. So I'd like to give us a short video tour of the water treatment facility in our Belgium data center. Oops, there's supposed to be sound here.
Sound plugged in?
Yes, it is. Okay. At our data center in Belgium, the Nimy-Bleton Canal on the north side of the site serves as the source for raw makeup water. The intake chamber is protected by a steel dolphin unit, which ensures the intake will not be blocked or damaged by ships or large debris. The intake chamber has two stainless steel intake pipes with isolation valves. Each intake is sized for 100% of the total site capacity. A compressed air tank periodically discharges across the bar grates to dislodge any material that may accumulate. Downstream of this intake chamber is the metering chamber to allow access for the local water authority. From here, water flows to the distribution chamber where initial solid settlement and hydrocarbon sensing takes place, and then flows into the 20,000 square foot water treatment plant. The plant consists of three main lines, each capable of treating cooling tower makeup water for 1/3 of the critical capacity. A combination sand, oil, and grease separator receives the water as it enters the plant from the subgrade piping. Aerators are used to disturb the water during the separation process. A conveyor removes the sand from the fluid, and the suspended solids are skimmed off and deposited into containers to be recycled. With most of the solids removed, the water is passed over a lamella clarifier so the remaining particles will settle out. This clarified water then flows over a V-notch weir and finally out into an open-topped polyethylene buffer tank. The buffer tank provides a net positive suction head for the pumps below. Sludge removed from the settling process is emptied to a subgrade sludge chamber. From this chamber, centrifugal pumps move the sludge to a cyclonic separator to remove all the water. Once the sludge is dry, a screw conveyor deposits the material into storage containers for removal. This dried sludge is used for landfill and as filler component for cement manufacturing. The piping to the various tanks and process equipment within the plant is interconnected for redundancy and concurrent maintainability. Duplex pumps are used to pump the clarified water into sand filters. The water trickles through the beds of sand in the filters and is further clarified in this process. The treated water is stored in 3 above-grade water tanks, where chemical treatment takes place to control microbial growth. The water is pumped from the canal water treatment plant to the cooling modules via underground parallel redundant distribution pipes. A distance of 30 feet separates each pipe, and the mechanical yard is fed from both lines in a looped fashion for increased redundancy. Samples of the canal water before and after treatment show the effectiveness of the water treatment plant. So just to remind everyone, the Belgium data center is also the chiller lists data center. So on 100% evaporative cooling with 100% reuse water from an industrial canal, we've been running this facility in production now, serving traffic for about 6 months. Thank you very much.
Hi there. Oh, there we go. I have a couple questions. One, when you say that the water is consumed, you mean evaporating goes in the air, right?
I'm not taking into consideration, Mike here, but I'm not taking into consideration it might be redeposited as the form of rain.
Okay, yeah. And secondly, you mentioned, I believe that you said, upstream, the power generation plants are using a lot of water, presumably in a similar sort of capacity, right? Where they use it for cooling their...
Yeah, whether it's once through cooling or not. The vast majority of it is ultimately returned to the waterways, but there is still a few percent that's lost.
And that just lost
right.
to the evaporation.
That's
so,
right.
So you mentioned then, in the non-Belgium data center, you said it was, water self-sufficient or whatever. It was using wastewater from one of these power plants?
No, not from a power plant. From the local water and sewer authority, we take basically the effluent from their water treatment plant.
Okay.
And
yeah, I wasn't sure what you were right. saying there.
The other thing to note is that the treatment plants don't make the water potable. So we don't treat it to a level of potability. We treat it to a level for industrial use where it's good enough for cooling towers, but it does not take place or take the place of our potable water supply for our offices and other water on the data center side.
Yeah. And my final question is,
I wouldn't drink that.
Yeah, I hear that. The final question is, you're considering that as sustainable because you don't think that will ever dry up. You don't think that industrial canal will ever dry up. You're still using the water. You're still evaporating the same amount of water. It's just you're more confident in the source. Is that why it's a sustainable thing, or could you elaborate on that a little bit?
Yeah, it really is that we want to be self-sufficient from the potable water supply used to kind of sustain the growth of population and to sustain the growth or for other uses. So our goal is to not take potable water from the local authority and use that for our industrial use.
In virtually all communities, fresh water comes in from some source, aquifer or river or, whatever, and then gets used and gets thrown away, right? And we want to hang off the thrown away part so that the net increase in the community is zero of the inflowing potable water, right? And assuming that the community doesn't go away, that water really will be there, to be reclaimed. So remember, every time you flush your toilet, you help us cool the data center.
Yes.
Hi, Mark Thiele from VMware. Just a curiosity question. Most of us are still forced to look at what the ROI will be long-term for any investment like this. Yeah. How did you guys do the ROI on this particular project?
So much to the kind of the same rationale that Olivier was talking about. From simply an ROI calculation, because water today is so inexpensive, it's not compelling. It really isn't compelling. So it was more about doing the right thing, sustainability, and also about business continuity and guaranteeing our access to water. What if the water authority in the area said, we're going to cut all of our industrial users by 50% because of severe drought conditions? Mm-hmm. By distancing ourselves from that impact, we kind of assigned a value to that business continuity in our TCO model.
totally support it. Just most of our business managers
It's-
won't, unfortunately.
Well,
So there actually are geographies where you can make a fairly compelling argument. So we've looked at that. One of our facilities actually, I think the argument is, within a hair of anything that would satisfy finance, and so with a little bit of increase in the rate, which if, for example, droughts happen more often in the U.S., you'd really be comfortably there, right? In other places, water is incredibly cheap,
Right.
and no payback period will ever.
Right. So long-term threat, basically, scare
And,
the heck
and,
out of
and
them.
really, the economics in Europe as well, water is actually considerably more expensive than here. And then with scale, the water plant per gallon cost actually comes down quite a bit. So scale helps you there. And in Belgium, the situation was particularly ideal because there was no pipeline that needed to be built. So this canal is literally 100 yards from our property.
Right.
And so that reduced the construction cost quite a bit as well.
Not trying to take away from it either. I applaud the activity.
no, it's the exact same type of analysis that anyone would have to go through. And certainly at scale, it makes more sense also.
Yes. And we have a project that's not live yet that will be clearly ROI positive with rainwater collection on the site, and that is very easy to justify just purely from a cost basis. It's extremely cheap.
I got to ask, I saw a lot of 80% type of motors there. How are you, your Belgium data center, how does that work out on your PUE if you sum all that inefficient gear?
I'm sorry, 80% what?
80% PF motors, 80% power factor motors, and essentially you've got a plant that is not very efficient.
Right.
So we don't. Sorry. Go
No,
ahead.
I was going to say is that we don't actually calculate the PUE of that water plant right now. It is a good point. Those motors are not very efficient overall.
But there's two reasons for not doing that. One is that everyone else doesn't count sort of the embodied energy of the things that are brought to the site, like water, in the PUE calculation either. Second point is really that in the grand scheme of things, the power usage of that plant is epsilon relative to the site, because yes, you have a bunch of pumps, but they're 100 horsepower pumps kind of thing, so it's hard to really make a difference. So even if we did count it, I doubt that once we have some IT load there, it would really show up in the stats.
Right. The entire plant has its own dedicated backup generator as well, and that is a very small portion of the overall backup generation that we have on site.
So I'm John Stanley with Uptime Institute,
Hi, John.
and my question is, it seems like there's kind of a high number and a low number for the water consumption of electricity production. You can get the high number based on how much do you have to draw, but then if you multiply that by the 2 to 3% that actually goes out in evaporation and consider the rest as kind of returned and therefore not consumed, then you get a low number. So in your earlier graph on saying that a waterless data center with a PUE of 2 actually uses more electricity than a efficient Google evaporative cooling data center.
Uses more water.
Sorry,
Right,
yes, you're right.
yeah.
Uses more water because of the water consumed by electricity. Is that using the high number for electricity water consumption or the low number?
That was using the from the National Renewable Energy Labs. They report a weighted average on the U.S. of 2 gallons evaporated for every kilowatt hour of electricity produced, and that was used in that calculation.
Okay, so that actually sounds like the low number.
It was the evaporation. It was not the total. It was just the weighted evaporative consumption.
Excellent.
All right, one more question.
Hi, Ted Height with Target. How about 2 quick questions? The chemicals that you use for treating that water, then it goes back into the canal when you're done with it. Is that all environmentally friendly chemicals that you're using? It's not molybdenate?
So what we're doing at the water treatment plant itself, it's only just treating for biological growth, for microbial growth. Once we take the water to our tanks for the cooling tower makeup water, we actually do treat it for the normal, suspended total dissolved solids and the rest.
Okay, and then on a data center where you use mostly evaporative cooling, but you have chillers too,
Mhm.
and these are offline most of the time.
Mhm.
Are you running pumps or something to get water treatment through those chillers, or
So we have a bypass loop that would take the water supplied outside of the chiller loop entirely when we're running on basically economizers.
got it? Thank you.
All right, thank you very much, Joe. So Luiz is going to add some concluding thoughts, and then we have a special presentation afterwards with a topic that was not in the agenda.
So I'm not going to take more than just a couple of minutes. I just thought it would be a good idea to sort of do a quick summation of the whole day, at least for my pair of eyes as an observer for most of it. First, I guess on behalf of Google, I want to thank you all for coming here. I think that we had, because of your participation, and particularly because of the presenters and panelists we had here that are not from Google, an event that was much more interesting than sort of Google disclosing sort of some details. And I think that this made it sort of much more interesting for all of us. I'd like to thank you for this. I wanted to, again, mention that you met some of the folks that were responsible here for all these new disclosures. Some of them that I think you agree they're quite interesting. A lot of them are here in the room and you've been able to talk to them. And a lot of them are not here as well. This is the work of a very, very large organization, including our data center operations and platforms design team. So I want to make sure to sort of remind us all of that. This is sort of an effort for a large company. Some of you guys actually gave us credit for breaking organizational barriers in the way that we find solutions for our problems that are really sort of looking at the large scope of things. And I want to just embarrass Urs here then for a moment and claim that, Urs Hoelzle is largely to blame for this. He's having a software guy, in particular compiler guy, run your operations is probably a good thing in terms of aligning incentives across an entire company. I wanted to close then with just summarizing a few thoughts that sort of kept coming back sort of throughout the day. One of them is that clearly I think you agree with some of the comments we made earlier that a lot of the improvement that you've seen in our data centers that were detailed here for the first time are actually achievable by a lot of people, perhaps everyone. Maybe not down to the percentage levels that we went to, but way better than sort of industry averages. And we're hoping that the kind of disclosure we do today will sort of help create incentives and targets that are more aggressive for people to do that. Some of us mentioned, or of you asked earlier, why is it that we're talking about these things right now? I just wanted to repeat what Jimmy Cladera said a little bit earlier today. It's way more fun to talk about this than it is to keep things secret. So trust me, we'd like to be able to disclose as much as possible. We are cognizant of the fact that good solutions have to have a strong economic impact, like Ken sort of makes a point of reminding us, and has to make sense for businesses. These are things that are actually done by people who are idealists as well, who sort of want to do good things too. And these things actually are sort of fairly well aligned. We want to run a profitable business that happen to be able to do sort of good things in terms of efficiency. Disclosing the kind of data we do today, I think that one of the main motivations is that our work with the EPA has made very clear to us how important it is to show, existence proofs of things, right? And I hope that you take that in that spirit. But basically, the solutions are the ones that sort of all sort of very well. The bag of tricks is the same one, right? You sort of understand climate effects. You control sort of airflow as much as you can. You try to use chillers as little as possible, for example. You pay attention to water usage. You look at the whole picture. The observation that Joe sort of made just now, I think, is a good example of that. If you look at just your consumption of energy and you look at water usage, some solutions may look better than the others. And when you look at the entire pipeline where the electrons come from, the situation is a little bit more complex, right? And sort of looking broadly at problems is something that kept coming on and on throughout the day that I think was useful to think about. Pushing our equipment a little bit warmer, right? James talked about this, something that, as you notice in our design, we have taken advantage of. And it turns out that if you actually look at a lot of electronic equipment, we had a paper a while back that looked at failure rates for disk drives, for example, that some of you may have seen, that actually look at our entire fleet of disk drives and ask themselves the questions: what happens if you run these things 5 degrees a little bit warmer? Is the sky going to fall? And it turns out that it doesn't, right? And so there are certainly opportunities that we need to take advantage of that are in that space. And then finally, Olivier mentioned this at least a couple of times, and I think it's important for me as a software engineer today. I go back between sort of the hardware and software side of things. I need to mention this too. These big machines are running software, right? The useful work that they do is the software that's written on top of them. And the best facility and the best managed and operated facility that's running crappy software and is not doing anything for you is not going to be a very efficient one, regardless of how good that PUE is. And it has to be possible. It has to be something that's possible for engineers with not a tremendous amount of effort to write programs that are energy efficient on your facility too. So part of delivering that whole platform is not creating a system that, well, you can save energy, but only 2 programmers in the whole world can design the software that will save energy on that facility. Those are not acceptable solutions. So I wanted to close the loop with that and pass the baton to Urs, who's going to tell us about some sort of new exciting projects.
Thank you, Luiz. So we have talked a lot about what we've done, and many things that we've talked about are things that already have been done, that were done 5, even 6 years ago. And I thought it would be good to conclude by giving you a little bit of insight in something that we're doing right now. So literally this week, people are working on it. And the topic is oil-cooled data centers. Now, you may think, what the heck, right? But it's not actually that crazy an idea. So oil has been around for a long time for cooling, transformers, right? Car engines. Oil has great properties. It's not corrosive. It doesn't conduct electricity, so you can embed stuff in it. Non-reactive. The problem is that it's really inconvenient to use, right? And that's why nobody's really used it. And that's why also for a long time we haven't really thought about this, because the oil is actually relatively expensive if you need it at volume. The containing the oil is even more expensive, right? And then to add insult to injury, if you try to do it, the AHJ comes and says, actually, you need a major permit, and it's going to take you 5 years to get that permit if you actually want to do that, right? You all know that from emergency storage. Turns out there actually are answers to these problems. And the answer are oil tankers, right? Oil tankers are custom built to hold oil. And The Economist actually just had an article 10 days ago about the cost of shipping drastically collapsing in the past few months. So in literally since last summer, basically the market doesn't exist anymore, because all these ships that have been shipping worse from China or oil from Saudi Arabia really are not very busy anymore. It's equally easy to park these ships somewhere. And, you all heard the rumors about barges on the ocean. One of the problems with having things on the ocean is that your power and your connectivity is far away. If you actually have the boat in harbor, these problems go away. The engines still are very useful. These ships have powerful engines, and all you need is an alternator for them. And then finally, you don't need to pay for the oil. You can basically rent the oil. There's many places. If you go to any major harbor facility, you see these oil storage tanks next to it. Oil flows. Oil isn't really stored in there. Oil flows through there. Right? And so you can get, with the right contractual arrangement, someone to flow oil through your container, right, your ship, instead of one of these big tanks. Now, it still sounds crazy, and I'm going to show you why actually it isn't. So here's an overview of a typical tanker, very simplified. And a tanker basically is, a hull and a bunch of individual oil tanks in it, right? There's really nothing very interesting. It's very simple. That's why actually the $7 million that I mentioned is literally a scrap value of the ship, right? And you can go look it up in The Economist. These ships are selling for scrap value today, right? Try to build these this kind of volume yourself, even in a warehouse, you're going to spend more than $7 million today. It's a very attractive housing. Now, what can you do with it? Well, very simply, you take the tanks, you put your containers in those tanks, right? I don't know what's so funny about that. So you don't fill the tanks fully because all you need is to get the convection cooling going on that oil. So really the conversion cost of that is very, very low, right? You literally need to bolt down the tanks, the containers, supply power, and you're basically done except for the UPS conversion. And the really cool thing about that is even compared to our efficient facilities, you eliminate a whole bunch of stuff, right? There's no air moving, there's no air handling, there's no coils, there's no pumps, there's no water, right? There's really everything basically disappears. And convection cooling takes care of it because these ships are very, very poorly insulated, right? Nobody pays any attention to insulation, of course. And so as a result, you just dissipate that heat into the ocean. So we actually bought one of these ships about 3 months ago. The logo is fake, right? It's not actually painted there, but we felt it was important to have it there. And we invite you to join us on a tour of the ship that's moored just about 10 miles from here. Buses are leaving after our reception today. And yes, no pictures, please. You need a special ticket. You can get it on the way out, actually, from people wearing red shirts like this one. We have 100 seats, so it should be plenty for everyone. But please get a ticket before you line up. We are going to have a reception now so that people can mingle. It's going to be where our lunch was, so we can kind of wander over there, has some drinks, cocktails, appetizers, things like that. And so get your ticket on the way. Thanks again for coming again, and we'll stick around to talk to you about that.